Now that we've covered both classical mechanics and quantum mechanics, you probably noticed that quantum mechanics was a rather unfamiliar picture of the universe. Now we focused on the mechanics of the basics of the theory, with an emphasis on doing calculations, and the way in which the principle of least action emerges from the quantum theory as the energy scale gets large. In some sense, once we realized that things were described by waves rather than particles, the rest of the theory may not have seemed so strange, and indeed, behavior that seems extremely odd for a billiard ball is very natural for a wave. But that's largely because we didn't emphasize just how counterintuitive a lot of the behavior of this measurement postulate is, along with the deeply non-classical behavior exhibited by entangled quantum systems. Talking about which ideas you have to give up before we focus on what has to replace them might have left us particularly lost and confused, however. In fact, that kind of confusion is quite common in popular culture. The fact that quantum mechanics defies common sense is often used as justification for a large variety of mysticism or pseudoscience. For example, the Heisenberg uncertainty principle and the language of it is used well outside the context of physical systems and non-commuting observables. But that doesn't mean it actually applies to them. And the fact that the cosmos doesn't in fact pander to our intuition based on a very specific set of circumstances doesn't mean that anything goes. It means that we have to look more carefully. We have to not trust our intuition. We have to not trust our instincts. We have to look and really observe and take that in. Find the quantum world in the quantum woo, if you will. Now, physics hasn't always had this reputation for being so counterintuitive. That reputation actually began many decades before with the advent of the theory of special relativity. Social, theological, and ethical absolutism was rife for many centuries, particularly in Western culture. And the idea from relativism that truth is relative to your point of view was seen as a very powerful challenge to the status quo. Now, in some sense, it was just a coincidence that the theory of special relativity and the language used in it had some kind of resonance with those ideas and with those challenges that were happening at the time. But at its heart, special relativity did indeed change our view on one thing from a very absolute view, something that's true and the same for everyone, to something that really does change on your point of view. And that thing is space-time. Now, if you say relativity to a physicist, they'll instinctively think you mean the theory of special relativity or general relativity. But in fact, relativity as a concept has its roots several hundred years ago in Galilean relativity. Now, you can understand Galilean relativity in various different ways. One way is to say that position is always described as relative to something. So there's me. If I ask the question, where am I? Supposing I'm in deepest, darkest space and there's no other matter in the entire universe, the question, where am I, doesn't have a very important physical significance. I'm here, I've got nothing to relate that to. It's only once we introduce something else, for example, over here, I have a bear. Now I have an important piece of data, which is how far away I am from the bear, who presumably, since there's nothing else in the universe, is quite hungry at this time. And so this distance, and this direction, is described by a vector, but notice it's a relative vector. So I might describe that by the position vector, the position of Joe with respect to the bear. Okay, and that would be putting the bear at the origin, and that vector would be going to me. And then if I have something else, I might have a piece of lettuce. Turns out I can't draw lettuce. But now I could do the position of the lettuce with respect to Joe, or I could do the position of the lettuce with respect to the bear. And you can immediately see from this diagram how that's going to work out. You can see that the position of the lettuce with respect to the bear is equal to the position of the lettuce with respect to Joe plus the position of Joe with respect to the bear. And because time is universal for all these objects, if I want to talk about velocities, if I have an object traveling, so suppose my lettuce is traveling at a certain velocity of the lettuce, again, I can't just talk about the velocity of the lettuce. I have to talk about the velocity of the lettuce with respect to something. Supposing we just have the lettuce and nothing else, it doesn't mean anything to say how fast it's going. So the velocity of the lettuce might have to be with respect to the bear. So if the bear and the lettuce are moving at the same velocity, then they have no relative velocity. But the velocity of the lettuce with respect to the bear, again, is going to be equal to the velocity of the lettuce with respect to Joe plus the velocity of Joe with respect to the bear. And that's just the time derivative of this equation, really. Now, we've introduced a really important new physical principle here that we haven't made explicit. And indeed, that's the principle that Galileo made explicit in his relativity hypothesis many hundreds of years ago. And that is that if the velocity is only defined relative to other objects, then we could never do an experiment that could tell what it is. Because that means if we did an experiment and it behaved differently depending on what velocity we had, the fact that we have different velocities with respect to different things would mean that things would behave in multiple ways. If I was bouncing a ball, the way the ball was bouncing would tell me how fast I was going, then it would have to bounce in multiple different ways because I'm going at various different speeds. In other words, there's no absolute velocity in the universe. And any two observers moving at constant speed and direction with respect to one another will always obtain the same results for all mechanical experiments that they do.